DICE is a distributed, interactive cube exploration system. It helps perform interactive slicing and dicing of large-scale datasets. It achieves sub-second latencies on datasets up to 1 billion tuples. It executes queries on a sample of the data at the user-specified sampling rate and returns the result along with the accuracy rates. In a number of OLAP scenarios, such as management of cloud infrastructure, queries are likely to be part of a larger session and not one-off random queries. We define a set of traversals for such queries. DICE provides speculative execution by running the most likely speculative queries during the time a user peruses the results for their current query, which our experiments show reduces latency by up to 30%. The architecture of our system employs a hierarchical master-slave approach. The data is present in the form of table shards at the slaves, which also contain LRU caches, where the results of hitherto executed queries are present. The user executes a query via the front end. The front end issues queries to the master, which federates it amongst the slave nodes. Once the queries return, it issues speculative queries, which are the most likely follow-up queries. The slaves execute the queries till their cache is filled or all of the speculative queries have been executed. If the next user query is part of the query cache, the results are returned from the cache. Otherwise, the query is executed. Now we look at the faceted exploration model. A facet consists of a single group by and multiple where predicates. Generalization of one of the where predicates results into a parent traversal. Adding another where predicate results into a child traversal. Changing a value of a sibling dimension causes a sibling traversal. Switching the grouping dimension with one of the dimensions involved in the where predicate gives us a pivot traversal. Now let us move on to the demo. First, we look at the various features of the front end of DICE. The left side configuration panel is used to configure the application. Here we can set the sampling rate, the algorithm, and the dimensions of the data cube. The slider allows you to change the sampling rate for each of the queries. Below the slider is a radio button where we can choose between using speculation according to the DICE algorithm or not. Below the radio button is a text area where we can specify dimensions for the cube. As new dimensions are added or removed from the dimensions list, Cube Lattice, which respects the dimension hierarchies, is dynamically computed and rendered in the Lattice Explorer below. Hovering over a region in the lattice will highlight the region, as well as the traversals possible from that region, as enumerated by our faceted exploration model. The highlighted point in the lattice shows the current view that the user is analyzing. Now we move on to the interactive query editor, which executes a query in one of two different modes, manual mode or assisted mode. In the manual mode, the user enters a query and then clicks on execute. In the traversal mode, the user chooses the next query amongst all the possible following queries. Below the text box are given the different features of the output, the overall execution time, the cache hit rate, and the status information of the previously executed query. The execution time is split between the time needed to actually run the query, the time needed to aggregate the results, and the network overhead. Next to it is a cache hit rate. It shows the percentage of user queries that had been cached. This is a great indicator of the effectiveness of speculation. If you click on the execute button, the current query will be executed with the specified algorithm and sampling rate. The results will be displayed in the viewer below. The viewer shows the output of the currently executed query, with the y-axis representing the measure and the x-axis representing the grouping dimension. The overall execution time for the query is primarily dominated by the back-end execution, with the hit rate of 0% since speculation has been turned off. Now let's try the traversal mode, wherein the system suggests all possible traversals from this current view. We can explore the parent traversal, which is a rollup. An interesting point to note here is that the results appeared immediately followed by the error rate, which shrunk each data point into a smaller size. The overall execution time for this query is around a second again, with a 0% cache hit. Now let's make another traversal. This time we will make a child traversal that is drilled down on zone. As we can observe again, the initial data points appeared as large circles, followed by the error bars, which shrunk the circle into a smaller size. The overall execution time for this query is also over a second, with 0% expected hit rate. Before switching to DICE algorithm, let's make one final sibling traversal for the NoSpec algorithm. As you can see, all the traversals for NoSpec took around a second again. Now let's switch to DICE experiments and see how it compares to NoSpeculation. We select the DICE experiment using the radio button, and we will start off with the same query as we did in NoSpeculation. The execution took around 1 second with a 0% hit rate because the cache was initially cold. Let's make the same traversal for NoSpeculation. Execution time for this query is almost half that of the NoSpec. This is so because the query had been completely cached during the time the user spent in analyzing the result. Now let's do the second traversal, which is the child traversal that is drilled down on zone. Now the execution time was almost 1/3 of that of NoSpec, with a 100% cache hit rate. Now let's make the final sibling traversal. Again, we got a 100% cache hit rate with the execution time almost 1/4 that of NoSpec.